Hi everyone, this lesson is for Algebra 2 Honors students. We are Chapter 5, 5-3, Quadratics. This picture right here is a photo taken at the Bean in Chicago, and just another example of quadratics in life. And this is just a very spectacular art exhibit that is just amazing if you go see it, and it's really cool underneath and inside. So just think about it, just like you to think about where you've seen parabolas and in life and relating that to you, right? Okay, so just going to start off with a warm-up of quadratic application. So we did a problem, some things very similar to this in class, but remember with the river along the side, so that the farm animals didn't need a border on that side because of the river. It's similar to that because we don't need a border on this side because we're going to use the barn as like the border. So what we have two long sides and we have little sides in the middle. So these are going to be this is my y and this is my y here. And then I've got little x's here. So we've got our x's and y's. And so I have 500 feet of fencing that you probably figured out in your groups. And therefore, I'm going to have an equation for perimeter because I have two variables, I need two equations. And one is going to be my perimeter and one's going to be my area. So for my perimeter, I know that the perimeter, which is 500 feet, is equal to, we have 2 y's plus 3 x's. And so I see that is linear. I'm going to move that 500. I'm going to solve for y. And so I'm going to get 2y is equal to negative 3x and then plus 500. I just moved that over to the other side. Dividing by 2, I get y is equal to negative 3 halves x plus 250. So right now, I know this is what y equals. Now I'm going to plug that into the other equation, which you're like, what other equation? Well, that's the equation for area. And because I know that the area is going to be equal to length times width, x times y, right? And in doing that, I do notice that I have a y value here that, look at that, I can replace with my other y value. So we have the area is equal to x times y. So we have x times our y value, which is negative 3 halves x plus 250. I'm going to distribute that x so that I know that my area is equal to negative 3 halves x squared plus 250x. So there's my equation. And look, it is quadratic. It also is a negative quadratic, and also something that you might see is that the y-intercept actually is at 0. So in graphing something like this, okay, I'm going to bring this down here. A couple of things that you might notice. Number one, you are going to start at 0, 0. And in order to find, and then it is going to go up and down because it is a negative parabola, okay? So what we're looking for are a couple of things. We want to find this value here because that's going to give us our domain. And yes, we do want to know what our domain is. And also, we are going to find this value right up here, which is our vertex. I want that number because whatever value across this is, right, that's half of my domain. And the max value up here, okay, that's my max area. That's that space inside. That's how much space I can fill with this equation. So you can use your quadratic, you can use your Desmos, and you also can use your quadratic, your graphing calculator. And I'd like you to try that. So pause for a moment to try to plug that in. So one thing that you probably figured out is when you typed in your equation, which I have, negative 3 halves x squared plus 250x, you probably realized that the graph in the window, where is it? And so you've got to think about this, in that we are talking about a very large area. But if you go to your menu, because you are going to have to change your window, and in changing my window, and of course you can zoom out or zoom in to see where your graph is. I'm going to start off with 0, and my x max, which I'm going to just say, I'm not sure. I'm going to say 600. That's how far over to the right on the x-axis I would go. For y, I don't have a minimum. It's just going to be 0, right? Because I'm not going down. It starts at 0, 0. And my max is not going to be 11. My max is going to be, I have no idea. So I'm going to say 6,000. And so I'm going to type in 6,000. And I'm not, let's see what happens when I do that. Okay, so if you can see, for me, 6,000 actually wasn't enough. Because see, there's my parabola. And see, it's actually going way, way, way up there. And it looks more like 11,000, is where that value is up there. I want to find that vertex. And so in order to find that vertex, yes, I can use the vertex shortcut. Yes, I can complete the square. However, I also want you to be able to use this to find the max value here. So this is what I'm going to show you. Again, I know we did review this. We're going to go to Analyze Graph. And then when we go to Analyze Graph, we want, because it's a high point, it's a maximum. And so I'm going to click on that and I'm going to go across to the right and try to find that maximum point. And it does tell me that it looks like 83.3 comma 1.04 to times 10 to the fourth power. That's what that means. If you can, let's see, let me move this out of the way. 1.04 times 10 to the fourth power. So what that means in reality is this, that my graph for here, okay, short-term memory here, 83.3. Okay, so we've got 83.3, and then we've got, I think it was 1.04 times 10 to the fourth power, which means take that decimal and go 1, 2, 3, 4. So that's 0400. So it looks like it's 10,400. So my max area that's what it is, 10,400. Okay, that's one answer. The other answer that I'm looking for is what's my domain. And so my domain would be, if this is 83.3, I'm going to double that, right? So 83.3 times 2, 6. You've got 6, and then 160, and then over 1 over 1. So about 166.6. So it goes from bracket, domain, my domain is going to go from 0, including 0, all the way to 166.6, and then and ending. It does include that value, so that is a bracket. Alrighty, that's my domain. Okay, and well, my domain that we're using for this problem, because we don't want anything in the negative realm, even though it keeps going. Okay, but that's our domain. That was a long warm-up. I got it. So we are going to switch between vertex and standard form. We're going to talk about just the quadratic formula. We're going to talk about solving application problems. Check, we did that. And we're going to talk about transforming quadratics today. So we are going to do another one of these review problems, and you've done that. This is find a quadratic function that has this vertex. So this vertex is going to be y equals a times x minus h quantity squared plus k, and where h comma k is my vertex. And if they gave me my vertex, that's that right there. So I have y is equal to a times x plus 2, that's the opposite, and then plus the same, k. And so now I still have 3 unknowns, but I do know a point, which is 7, negative 1. So we're going to plot that. Negative 1 is equal to a, don't know what that is, and then 7 plus 2, quantity squared, and then add 6. So we've got 9 squared, which is 81. So we have 81a plus 6 equals negative 1. We have 81a is equal to negative 7. And therefore your a value is equal to negative 7 over 81, in which case we plug it back into this equation right here, and we say y equals negative 7 over 81 times x plus 2 quantity squared, and then add 6, and therefore we have a vertex our equation for our quadratic is in vertex form, and you're going to see this in another place. Definitely. So we are going to get started with this is a derivation of completing the square. I'm going to start you off. I will say this one thing. You're trying to solve for x, which means your y needs to go to 0, which means to start off, you're going to have negative c here. And I want you to try to do this for homework. And this right here would be a problem of the derivation of basically how did we get from here to the quadratic formula. So we are going to do this at one point. I just wanted you to get started on this. This is definitely something that you need to finish for homework. So we're going to start off on transformations. And when we're doing transformations, we are going to be trying to take our values, our parent functions, and then adapt them differently. And so we did this, and I would do this in class if I was with you. And then just to remind ourselves what our parent graphs are in our for our dancing mathematician. But being more specific, your identity, if you have this function right here, this is your y equals x. And it's all of these are f of x because they're saying, hey, this is a function. And so we have a function of, starts at 0, a slope of 1, but this is my identity function, is parent graphs. Quadratic, check. Reciprocal function, we've done. Revisiting, we have asymptotes here, or you can't touch that, and here, or you can't touch that. You have your square root function, which if it looks like this, will start at 0. However, anything underneath, like if this root kept going and I said maybe -4, then this 0 would be transformed over here to translation for 4 over there, going that way. We have our cube root and we have our cubic. And then we have our absolute value. Because remember, your absolute value, normally, if it would come from our identity function, which said f of x is equal to x, which is our y equals x, right? Which looked like this. But because it's an absolute value, we can't have any negative values. And so they basically just kind of bounce off and then keep going that way. And then just starting with the most basic of x squared, we have reflections. Now, reflection is this. I mean, if I have a parabola that looks like this, let's say, okay? And I think I can do better. I'm going to try. If I have a parabola that looks like this, all right, and I want to do a reflection across, let's say, the x-axis, this is my reflection down here, okay? But if I want to do a reflection across the y-axis, that would be the exact same picture. If I want to do a horizontal shift, this graph would go to the left or to the right. And those values, by the way, of horizontal shifts, the horizontal shift, those values are inside the parenthesis like this, like x minus 2 or x plus 2 quantity squared. Whereas a vertical shift, that means I'm taking my graph and moving it up or down. That value is going to look like this, x squared, and then plus some number, whatever that is, but it's outside. A vertical stretch or shrink is similar to a horizontal stretch or shrink. So you could look at it both ways, but mostly, specifically, this is what you need to remember, that any number outside of your x, let's say x squared, that number right here, if the higher that number is, the steeper your parabola will be, okay? The smaller the number, the wider, okay, that your parabola will be a wide. It's almost like a slope, like a up 1, over 2. It's almost like that. So starting off with reflections, we have 2 types of reflections. Okay, the first reflection is where you have the value inside here versus y equals the outside reflection. Well, basically the outside reflection is across the x-axis, and the reflection inside here, that's across the y-axis, and that's the difference right there. Okay, and so if you were to graph those on your graphing calculator, and I do suggest that you do that, just helps you get more familiar with your graphing calculator, you would see that this one right here would look like that, whatever my parabola looks like at x squared, and that's just going to look exactly the same thing as if it started with a y equals x squared. Whereas this one, graphing across the x-axis, will look something like that. Okay? And just showing this to you, like what it would look like on your calculator, doing that, that's what it would look like for the negative inside. Again, it just, your y is It's just flipping across the y-axis like that. And then this one would be solve, you know, what it would look like on your graphing calculator if you just type that in like that. Okay. So the next thing here is just another example, but a root function with reflecting across the x or y axis. And what you're going to see for this one is your regular, you know, graph would look something like that for your parent function for your square root of x. However, this value, if it's outside, it's reflecting across the x-axis. So this one would now, my new graph would look like this. And this would be your negative square root of x. Whereas with the parent function like this, going to the right, if you were reflecting across the y-axis, because that value is inside, it's going to look like this. Okay. This right here is our vertical shifting up and down. So you're looking at that, and what you're seeing is your x squared. If you go up, you know, this is up 3. This one right here is down 2. And again, if you have the x squared function where you've got your quadratic where it's inside, the plus 2 is going to shift to the left. Okay, this is your x. This is this one right here. And then your minus 2 is this one, because that's going to shift to the right. And so that's that light green one. So just combining a vertical and a horizontal shift, let's say we've got the absolute value. We've got our parent function right here, which is this, and now it's blue. This value in here, see the minus 6, that means go to the right 6 units. So now we're shifting to the right. And so this V that I just drew would move over to 6. And then because it's down 4, would then drop down 4 units. And that's what this does down here. So the value down here drops it down 4 units. And then this moves it left and right. Now for this one right here, we start off, and this is an example of your horizontal stretch and shrink, which a lot of people call it a vertical, you know, stretch and shrink also, and they mean the same. You start off with your regular graph. Now the higher the number, so we've got the number 4. See how thin my graph is. It's really thin. Whereas if I said a 4th, now this graph is a lot wider. Okay. And so this graph here just has all 3 of the graphs on there. But just to note, it's more like it's almost like you can think of it like a slope where if it was 4x, and by the way, 4x squared would actually be 16x squared. And so for this one, that's like super high. That's like up 16 over 1. Whereas this is just, has no x. So I'm going to put that on there. So that's 1/4 x squared. So 4x squared looks something like this, and this is the vertical stretch and shrink, exactly the same thing. So let's see. For this one, this is just state the transformation. See all the different things that are happening. Number 1, we've got a reflection outside. So if it's a reflection, it's going to be, first off, we're going to say reflect across the x-axis, because that's outside. Then we have a translation of going left to horizontal shift to left. And then we've got a vertical shift going down 1. And so those are all the different things. So you would start off with a quadratic, which looks, let's say it's going to look something like this. And then the first thing you're going to do is we're going to do our reflection, and I always like to do those first. And so this is a reflection across the x-axis. Right off the bat, we're going to reflect this across the x-axis. There it is. So now we have that. And then what now is happening is we're going to shift it 2 to the left and then down 1. And then we have our new transformation. For this one right here, the transformations are going to be a vertical stretch of 1/3. It also means I'm going to take my parabola and go right 1, and then I'm going to go up 2. So let's say my parabola is now wider. Okay. I have no reflections. You always try to do the reflections first. So we've got a wider graph, like up 1/3. And now I'm going to shift my graph -1. So that's going to be 1 to the right. Okay, so I'm going to move it to the right 1. And then I have to move it up 2. Okay, so I'm going to do that. Okay, and so then that's it. So, yes, I do want to see all the 3 transition in the graphs. So you would have 3 different shifts. So you'd have the original graph that looked like this, okay, coming up. Then you'd have a wider graph, right, of the 1/3 that looked like that. You'd have a shift of 1 over to the right, so now it would look something like that. And then you'd have a final shift going up 2. So just a couple of things. We're going to start with a cubic, and this one is going to look like something like this and do this. And so for this cubic, now it's the shape y equals x cubed upside down. So I'm assuming that's reflected across the x-axis if it's upside down. So now that's going to go like this, and this is going to go up like this. Now, just a note on this one particular graph, by reflecting across the x-axis and the y-axis, give me the exact same function. Okay, and then I'm going to shift it right, and I drew over that, and it looks like it's a right 5 units. So now I'm going to go over 5, and then I'm going to redraw my graph, and then that would be done. For this second one, which is the square root of x, so that would look like that. It's reflected across the y-axis, so now it looks like that. It's shifted left 2 units, so now it goes like that. And then down 1 unit starts here and then does that. And so that would be done. And the last one is 1 over x, which, remember, is our graph where we have our asymptotes. And this right now, to start with, looks like this. Those are our graphs, okay? Now, if I reflect it across the x-axis, now this value here, I'm going to redraw it, is going to go down and over. And then this is going to go like that. Now it's reflected. Now it's green. And up 5 units, that means I'm going to take my axis right here, and then that's going to go up to 1, 2, 3, 4, 5. So now my new axis looks like this, but I still have my y-axis, still can't touch it, and then my new graph would go up like this and down like that. So you're going to show those values. So just trying to check, you can do a little Desmos fun stuff here. This right here, x minus 3, that's a one of these absolute values. Okay, by saying minus 3, what that's doing is it's moving my graph over 3 units and then down 4 units. For this graph here, what we have is a cubic. Now remember, cubics go up right, down left. This is a reflection across the y-axis. So that means now that my graph is going to go this way and down. And then the only thing that this translation is doing is it's taking this 5, the graph, and dropping it down 5 units, and that's what it would look like. And then lastly, for this one right here, we have a vertical stretch of -3. So this is a quadratic. So I'm going to start off with just drawing a quadratic like this, okay? And then we have a vertical stretch. I'm going to do that last because I want to do my reflection first, which means now my graph is going to be going flipped upside down, and it looks like that. It's also going to be shifted to the right 3 units, so over this way. And then it's going to go up 5. So that's what it looks like so far. And then the only other thing that I would do for this graph, because it's a 3, it's just going to make this a little bit thinner is what it is, okay? And just a note, if you're trying to find the actual, again, the y-intercept is 5. So just keep that in mind when you're looking at this. I know I made it. This is definitely not drawn to scale. So if I was going to be really, really careful about drawing this to scale, my final graph, after I shift it over 3, 1, 2, 3, up 5, let's see, I wonder what my actual y-intercept would be. Let's figure that out. X minus 3 quantity squared, add 5. So this is going to be x minus 3 times x minus 3. I'm going to do the little shortcut, which is x squared minus 3 is minus 6x plus 9. I'm going to multiply everything by -3. And I'm going to get negative 3x squared. I'm going to get a plus 18x. I'm going to get a negative 27 and a plus 5, which is more like the graph that I drew, because that's a negative 22, which is my y-intercept. So way, 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 way down here. So again, when I took my parabola and I reflected it across the x-axis, I did do this. I moved it to the right 3 and then up 5. And so realistically, keep in mind, see this -3, that 3 value in front is going to make my graph a lot skinnier, and so it looks more like that actually might go through the -22. So just a couple of things. We have a parent function, we have a reflection across the x-axis, we have a reflection across the y-axis, horizontal and vertical shifts, and then we've got our stretches and shrinks. And again, those two are going to give me very, very similar outcomes. So I did have another review problem, but if we have time permitting, we're going to start off our homework. We're going to do Desmos, the parent function graphs. I want to see you get started in class. So I'd like everybody to go to Desmos and get started with that. And in the meantime, yeah, we'll do that other value next week. Okay, so good luck. Thanks for watching. Hope it helped you.